Hello and welcome. My name is Jeffrey Newell. I'm the director of the Vanderbilt Kennedy Center at Vanderbilt University Medical Center in Nashville, Tennessee. And I'm glad to be here and thank you for the organizers for inviting me. Today, I'd like to talk about Rett syndrome, the road from recognition to treatment. I'd like to start with a brief history of Rett syndrome, which was originally described in 1966 by an Austrian pediatrician named Andreas Ретт, who had observed a series of children in his office who had similar features. He published this in an Austrian weekly medical newsletter, but it wasn't really recognized widely until 1983, when Bengt Hagberg and colleagues published this paper, which identified and clarified the clinical features of Rett syndrome and gave it the eponym by which we know it today. So Rett syndrome, in 2010, we created a revised diagnostic criteria that identified and reinforced concepts that were created by Andreas Ретт and Bengt Hagberg, which is this is a disease that has a specific characteristic pattern in which children are born relatively normally and have an apparently initial normal development, although with careful evaluations, you can find subtle abnormalities in retrospect. They undergo then a developmental delay where they no longer obtain skills at quite the rate we would think they should. Notably, they then have a regression, specifically with a loss of acquired purposeful hand skills and a loss of acquired spoken language. And this loss may not be complete. It may be partial, so they may have retained function. But importantly, there's a stabilization. And so that's the important aspect of Rett syndrome. There's a regression with a stabilization. People with Rett syndrome also develop gait problems or fail to learn how to walk or lose the ability to walk entirely. They also have characteristic repetitive hand stereotypies. And these are the core diagnostic criteria for Rett syndrome. We've learned that it's an X-linked disorder that primarily affects girls, and it occurs in about 1 in 10,000 live female births. Now, in 1999, Huda Zogby and colleagues identified the genetic cause for the majority of people who meet the clinical criteria of Rett syndrome, which is mutations in the X-linked gene methyl-CpG binding protein 2, or MECP2, which is a protein that binds to DNA and regulates the expression of other genes. With this information, we know that 95 to 97% of people who have typical or classic Rett syndrome, meaning they meet all the diagnostic criteria, have mutations in MECP2. Most of these mutations are de novo, meaning they're not found in either mom nor father, and really they're a singular case in the family. But importantly, 3 to 5% of people who meet the clinical criteria for Rett syndrome do not have identified mutations in MECP2. And we've identified other mutations in other genes, and there are genes such as mutations in CDKL5 or FOXG1 that have similar and overlapping clinical features to Rett syndrome, and they were considered to be atypical Rett, but we've recognized these as distinct disorders. Although this disorder primarily affects girls, there are boys who have these loss of function MECP2 mutations similar to those seen in girls with Rett syndrome. And classically, we've thought they have severe congenital encephalopathy, meaning they're affected from birth. However, we've been recognizing there's a much broader phenotype, clinical features in boys who have these loss of function mutations. And I think that we need to do more work in this area to better understand this. Now, we've learned that you can also duplicate and have an extra copy, so a gain of function of MECP2. And this also causes a severe neurodevelopmental disorder that primarily affects boys. Then they have autistic features and seizures, absent speech, and infections. So there are some similarities with Rett, but it is also a distinct disorder. Now, with the identification of the genetic basis of most cases of Rett syndrome, this allowed genetic engineering to engineer rodent models of Rett syndrome, and they remarkably reproduce many of the clinical features that we see in people with Rett syndrome. Now, most work has been done in male animals, which is not the exact best model for Rett syndrome, which occurs in girls. But importantly, female animals also have similar phenotypes. These are mostly done in mice, but rat models have been generated, and they also show phenotypic abnormalities similar to those seen in people with Rett syndrome. Now, importantly, in 2007, Adrian Bird and colleagues did a genetic engineering of a mouse in which the gene MECP2 was disabled, but they could turn the gene back on, and they could turn it on in a temporal fashion using some genetic engineering tricks with a Cre recombinase. And when they did this, even after the animals were sick, they improved. Their survival improved, and a number of their behavioral features improved. And that originally was done in male animals, but it's been subsequently reproduced in female animals. And it also shows the ability to restore activity. So this really provided the basis for the hope that we could develop meaningful clinical therapies that could improve the lives of people and modify the disease course. And shortly thereafter, in 2009, Profesor and colleagues treated animals with a tripeptide, so 3 amino acids that's derived from the amino terminus of insulin-like growth factor 1. And the 3 amino acids are shown in the middle. It's called glypro glue or glypromate. And when they treated the mutant animals with this, it improved their survival, it improved their locomotor activity, and it improved their breathing and their heart rate features. So this was very exciting that this could be an avenue for treatment. And this led to clinical development of drugs related to this insulin-like growth factor 1. And specifically, I'm going to talk about trofinetide. So the Profer's group treated with this IGF-1, which is the structure shown on the left. Trofinetide is exactly that same compound, except it has a methyl group added to it. And this improves the drug qualities, meaning it can be taken orally and has a longer half-life, so you can take it only twice a day. Now, 2 phase 2 clinical trials have been conducted with trofinetide in Rett syndrome in adults and in children. And both of them showed that trofinetide was safe, fairly well tolerated, and showed signals of efficacy. This led to a phase 3 trial called the Lavender trial run by Acadia Pharmaceuticals. And the results of this have been released, and it was successful. It met the primary endpoints that were specified. Specifically, the two primary endpoints were improvement on a caregiver reported scale called the Rett Syndrome Behavior Questionnaire, or the RSBQ, and a clinician scale called the Clinical Global Impression of Improvement, or the CGI-I. And in both of these cases, over time, at the end of the study, people on trofinetide showed improvement compared to the people who were on placebo. Now, that is very exciting. They successfully met the co-primary endpoints. They also met the key secondary endpoint, which was a nonverbal communication scale. There were adverse events, primarily diarrhea and vomiting, observed more frequently in people with on trofinetide compared to placebo. The sponsor has submitted a new drug application, or an NDA, to the U.S. Federal Drug Administration, or FDA, in August of 2022. And the FDA has said they will provide a response to this in March of 2023. Just mentioned briefly, concurrently, there's been development by a company called Anavex of Anavex 273, which is a sigma-1 receptor agonist, which showed benefit in an animal model of Rett syndrome. And they are also conducting clinical trials and have reported some promising top-level results. And we'll have to hear more about that as time goes on. Now, I'd like to take a step back and introduce something that will be a basis of much of the talk, which is the Rett syndrome and related disorders natural history study. This is a multi-site study, longitudinal study, that was run by Alan Percy at the University of Alabama, Birmingham, and I was the administrative head. It was supported by the National Institutes of Health in the US. Ultimately, we enrolled over 1,800 people. We saw in them longitudinally of over 8,700 visits, 14 sites across the U.S. And for classic or typical Rett, we saw 1,258 people, and they were seen over 6,800 times, with 83% of the people being seen more than once and 50% being seen more than 4 times, so an average of 5.4 visits. So we have a lot of information, longitudinal information. And I just want to point out how that relates to these other critical timeline of events in Rett syndrome research, with 1999, the discovery of the genetic basis, allowing the development of animal models, 2007, showing reversibility in animal models, showing there could be important treatments developed, the treatment with the tripeptide by Morganka Sur's group in 2009, and now the successful phase 3 trials in Rett syndrome. And importantly, the natural history study began way back just shortly after the discovery of the genetic basis of Rett syndrome. And some of the goals, really, of Rett syndrome natural history study is to develop clinical trial readiness for Rett syndrome. And what does that mean? Well, one is to develop a network of clinical sites that are able to do the kind of clinical research you want to do in a clinical trial. 2 is to characterize the clinical features and the natural history of the disorder. And 3 is to develop clinical outcome measures and biomarkers. So let's talk about having a network of clinical sites. Well, we had 14 sites across the US. They're shown here in the flags. We enrolled people throughout the entire US and also people from 20 different countries across the world. And this has been fundamental sites for the industry-sponsored trials. So I think that was very successful, creating this network of sites. How about characterizing the clinical features and the natural history of this disorder? Well, we've published over 50 manuscripts with multiple additional manuscripts in submission and preparation. And these manuscripts have covered many things, such as looking at genotype-phenotype relationships in Rett syndrome, looking at the clinical symptoms such as epilepsy, breathing abnormalities, hand stereotypies, sleep, scoliosis, and developmental delay in Rett syndrome, looking at growth failure and gastrointestinal nutritional issues. We developed Rett syndrome-specific growth charts shown on the left. We've looked at things like hand and other anthropometry growth, pubertal development, and then GI features and biliary tract issues and bone mass issues. We also looked at the behavior and the quality of life, which has been fundamental in also gaining additional information on Rett syndrome. And not to just end with Rett syndrome, because it did cover other disorders too. And so we've published a series of papers talking about features in MECP2 duplication syndrome, comparing across the disorders of Rett syndrome, MECP2 duplication syndrome, CDKL5 deficiency disorder, and FOXG1 syndrome. And we've published a variety of papers in that. And there are many more papers that are being prepared in this area. So let's talk about development of clinical outcome measures and biomarkers. So first, let's start with biomarkers. So biomarkers are things that you can measure in someone that would allow you to correlate with, say, disease severity, to identify people who might respond to treatment. And then importantly, I think, is to show things that would show improvement during a clinical trial before you actually see clinical improvement. So that would help expedite the way clinical trials are conducted. And I'm going to talk a little bit about one of the avenues that we did in the natural history study, which was using neurophysiological features. So these are EEGs. These are non-invasive, and they're fairly well tolerated. And I'm specifically going to mention things about doing what's called evoked potentials. And what this means is you provide some sort of stimulus and you record brainwave activities in response to the stimulus. And this example in this cartoon is showing what's called the visual evoked potential, where you have a flashing grid of light that is seen and you record from the brain, and you can look at, you do this repeatedly, and you can look at a characteristic brainwave response, electrical response in the brain, and that's shown on the bottom right, which shows the change in this activity where you have peaks that occur at a fixed set of time. So you have the time to the peak, which is called the latency, and the height of the peak, which is called the amplitude. And in the natural history study, we looked at people with Rett compared to typically developing controls. And we did both visual and auditory evoked potentials, where it's clicks of sound. And those graphs are shown on the left. And we can see that they were different from people typically developing individuals, primarily in the amplitude. They're shorter, their peaks are smaller. And so they're different from people who are typically developing. Additionally, we could show that it was correlated with clinical severity. That's shown in the middle. Now, my lab and other labs have gone on and looked in the animal models, and we can reproduce very, very similarly, these evoke potential response and other neurophysiological features in the mice. And we've shown that they also correlate with disease severity and progress over the time. And since we can do both things in both species, it offers opportunity to translate the findings between the species and to accelerate both preclinical and clinical research. So how about the development of clinical outcome measures? Of course, you can't do a clinical trial unless you have a good outcome measure. Now, we did work in the natural history study to help support the development of the clinical global impression scales. And I'll talk a little bit more about that later. But to take a step back, I think importantly is to think about when you have an outcome measure, you'd really like to measure what matters most to the people who are affected and to their caregivers. And within the context of the natural history study, we asked caregivers at every visit, what are their top 3 concerns? And we provided them with a list of 21 options. This list was generated through expert curation of the literature, discussion amongst expert clinicians, and then feedback and input from stakeholders from the International Rett Syndrome Foundation and other caregiver stakeholders. We also let people have an option of selecting other and entering a free text. And here's the results for the top concerns for classic or typical Rett syndrome. And this is just showing the top 10 concerns in ranked order. And I think importantly, you can see that some of the top concerns like lack of effective communication, lack of hand skills, abnormal walking, repetitive hand movements. These are the clinical features that are really define Rett syndrome. So it really makes sense that these are concerns that caregivers report. But importantly, you see symptoms such as seizures, number 2, constipation, sleep, breathing problems, bloating, chewing and swallowing. So there's more than just those cardinal features of Rett syndrome. There's these other symptoms that really matter to the caregivers. And it's important to think about when you develop treatments, they should really target these most important issues. Furthermore, if you have an outcome measure, you really want to assess those issues to make sure that this is really making a meaningful impact to the affected individuals and their caregivers. So what do we have for clinical outcome measures currently? These are the ones that are being used in the clinical trials that have been completed or ongoing. One is this caregiver scale, this Rett Syndrome Behavior Questionnaire, the RSBQ. And this is a 45-item questionnaire that the caregivers fill out. And it has these domains, which is more than just behavior, although it's weighted more towards behavior. Now, the advantages of this is that it's relatively simple to complete. It doesn't take that long, and it's understood by the regulators, the FDA and the EMA. The downsides is that we haven't really established the relevant differences that would be meaningful on this measure. And while it does cover a variety of domains, it does not necessarily cover all the top concerns well. Things like hand stereotypies and bloating are decently covered, but things like walking and hand use is not as well covered or fairly briefly covered, and other things aren't covered at all. Well, how about the caregiver assessed scale, the clinician assessed scale, which is the clinical global impression of improvement. Now, this is a fairly simple concept where you have a 7-point scale where the clinician evaluates how things have changed for the person in the trial. And it's the global impression, with 4 being that there is no change, and 3, 2, 1 being improvement, and 5, 6, 7 being worsening. This is also understood and accepted by regulators. But it's important that you have disease-specific anchors to help guide the raters, and we did develop those, and we also have to have a consistent training, which has also been developed and used in these clinical trials. Now, one of the downsides is that while it talks about improvement or worsening, it doesn't provide specifics of what was improved or what worsened, and so it doesn't really give you an information on that level. So the question is, can we use the natural history study to develop additional outcome measures? And so we did this from the data from the natural history study, looking at a rating scale that's filled out by the clinicians called the Motor Behavior Assessment Scale. And this is a clinician-rated scale that was used throughout the entire time of the natural history study, that had 37 items. Each item had what's called a 5-point Likert or ordinal scale, with higher scores being worse. And then we can create a combined score for a total score. Now, the issue is that this was never really evaluated. It wasn't developed as an outcome measure, and it wasn't really evaluated as an outcome measure. So we applied formal psychometric techniques using people who had classic or typical Rett. We had 1,258 people. We looked at their baseline visit, and we split it into a 2/3 development set and 1/3 validation set. For the development set, we use exploratory factor analysis to look at the factor structure, and the validation set would validate that. And from this, we developed the revised motor behavior assessment, or the RMBA. So this is 24 items that are clinician rated during the evaluation. These cluster into 5 factors, which is motor dysfunction, functional skills, social skills, behavior, and breathing problems, plus 3 important clinical features: seizures, rocks, hand stereotypies, and body rocking, that were included because we felt that they were very important. So overall, this had very good fit statistics. It also showed pretty good Cronbach's alpha, or internal consistency. Now, we looked at the validity of this by comparing to other clinician-rated scales of severity, like the Clinical Global Impression of Severity, where higher scores meaning more severe. And you can see that for the total RMBA score, people who had the lowest CGI-S, 3, they have a lower total RMBA than the people who are higher severity. So it climbs. We also compared it to another rating scale for severity in Rett syndrome called the Clinical Severity Scale, CSS, and it's very well correlated. We also showed that it had a genotype-phenotype relationship that we've seen repeatedly with things like R133C having a lower score on the RMBA on average as a group, compared to things like R168X, which is typically at the higher end of severity. So it's good consistency like that between the clinician scales. How about with the caregiver? So we looked at this compared to a quality of life measure, which is called the Child Health Questionnaire. And this gives 2 scores. One is physical health, shown in orange, and the other is psychosocial health, shown in blue. And you can see that the RMBA, as the score goes up, the score on the physical health goes down, and that means worse quality of life. We did not see a relationship with the psychosocial health, which also is consistent with what we've seen in other measures. It also, these RMBA subscales also correlated with caregiver-reported items that would be represented on the subscale, such as motor dysfunction, looking at things like ability to walk, bottom scoliosis, and there was a good correlation there. And we've then, on a small group of people, we looked at the RMBA subscales to the RSBQ, the caregiver rated, and we compared things like that we think would be correlated, like functional skills to hand behaviors, and you see good correlation, social skills to anxiety, and you see good correlation, breathing on the RMBA to the breathing measures on the RSBQ, and again, showing correlation. So that would be convergent validity, where the two things you're looking to see that something you think is measuring breathing that a clinician fills out is also what the caregiver reports. Now, look at divergent validity, where you say, how does functional skills relate to fear and anxiety? Functional skills in the RMBA to fear and anxiety on the RSBQ, and you see they are not related. So that's also important, because it goes along with you're measuring what you think you're measuring, you're not measuring something else. Now, we've been using the longitudinal data in the natural history study to develop growth curves, the expected rate of change in different age groups of the RMBA. And from this will allow us to make predictions on where things should be, and that will help us define what is a minimally clinical change in an intervention trial. So how well does the RMBA capture these important clinical issues? Well, pretty well, better than the other things, but it's still not complete. And the full range of functional skills on the RMBA, the range of options is not really as broad as we might like to see. So again, can we use the natural history study to develop a better clinician rating scale? And then can we also use the information to develop a better caregiver rating scale? And so we've done this. We've followed exactly the same process that I outlined for the RMBA to develop a new clinician-rated scale supported by Alcyon Therapeutics. We haven't named this yet, but it divided into 6 factors you see here with 31 items. So these represent many of the important things in Rett syndrome. We did the same thing for a caregiver-rated scale using caregiver-reported forms that were completed. And we're calling this the Rett Syndrome Caregiver Assessment of Severity and Symptoms, or the RCAS. This was supported by the Rett Syndrome Research Trust. And this had 4 factors: functional movement, communication, behavioral problems, Rett-specific behaviors, and 32 items. And the clinician fills this out. Now, we've shown that this correlates with the clinician-rated severity. So the caregiver fills this out, and it correlated really well with the clinician score at the same time, the RMBA. It also correlated with the genotype, where again, we see the higher scores on the left with R168X and the lower scores on the right with R133C. So we're being consistent. We also showed that it increased with age, and I'm just not showing that here. So how did we do? Well, I think we did good in terms of developing them. I think we've covered the items, but we're still missing items that are in the top concerns, like some of the GI issues like constipation, bloating, and gas. And we don't really have much about sleep in there. So the good thing, though, is that other groups have done things. We did it in the natural history study to look at just using standard sleep evaluations in people with Rett syndrome, and we showed that that seems to be able to be worked. And the Baylor group in Houston has developed a gastrointestinal health questionnaire for Rett syndrome. So these, combined with other things, can help assess those clinical domains that are of top concerns. Additionally, we think about having functional assessments like walking or hand use, and people like Jenny Downs and Helen Leonard have been working on this using video capture and scoring for hand function and gait. People like Bernard Suter at Baylor College of Medicine have been looking at using formal gait analysis. And then for communication, the group at Duke has been looking at modifying the observer-reported communication ability measure, the ORCA, which was originally developed for Angelman syndrome, to be appropriate for Rett syndrome. So I told you all this, about the clinical trial readiness, developing these outcome measures. And, the question is, well, what's next? I think it goes back to the work from Adrian Bird in 2007, the ability to show that you can reverse the disease if you turn the gene back on. And so this is something that has always led to the question, well, what about gene therapy? Why don't we do gene therapy? And I'm not going to go through all of the things. Stuart Cobb is talking later today, and he's been instrumental in doing this work. But here's just a few examples. It's been done repeatedly in animal models and showing that it works. And now 2 companies, Taysha has started a clinical trial of gene therapy in adults with Rett syndrome in Canada, and Neurogene in late January 2023 got clearance from the FDA to start gene therapy in children with Rett syndrome, and they say they're going to start a trial in the US during 2023. There are also a number of additional alternative ways that have been developed preclinically to reactivate MECP2, like X chromosome reactivation, read-through therapy, DNA editing, RNA editing, and even new things that are being developed. So I think there's a lot of promise and a lot of hope that we can develop new therapies. And so really the future, I think, is really bright. I think the success of the phase 3 Lavender trial of trofinetide is really promising. It shows that therapies can be developed for Rett syndrome and similar disorders. And there are new opportunities and new avenues of treatment that I think will start moving to clinical trials. And the natural history is fundamental in establishing the ability to do these clinical trials. And it's critical to understand what problems need to be addressed. And we can continue to use the natural history study data to continue to develop these outcome measures. Now, I just like to list and thank the people who were part of the natural history study, especially Alan Percy, through his vision that we did this. And then, of course, I want to thank all the people who participated in the trials, the International Rett Syndrome Foundation, who supported the natural history study, and all the people that I really learned about Rett syndrome from, which are all the patients that I care for. Thank you for your time.